if we have light, it's going to stick around, travel back and forth, and it's going to be confined to nanometer-sized dimensions, super confined light. Q by V will be high. If we do a little bit of modeling, we can actually see that in theory, we can get the electron to recombine with the hole before the electron reaches the conduction band minimum. And since we're competing with relaxation all along the way, we should get the colors of the rainbow, right? We're going to get a recombination event from here, from here, from here, so on and so forth. So that's the spectrum that I showed you before. Put an optical antenna next to your silicon, and you get this. It's huge. You get broadband emission spanning the visible range. And what does that actually look like? This thing lit up like a light bulb. This is silicon, a light-emitting material. So we've enabled silicon as a light-emitting material, but I think the true strength of this technique is that it's completely general, right? We apply this concept of engineering kinetics, of engineering electron-hole recombination with optical antennas, to two of the most opposite semiconductor materials that I can think of. An optical material here, and a dark material like silicon. Completely different. And to come back full circle, we began the talk, we motivated the talk with silicon optoelectronics. And to be quite honest with you, if we really want to have optical on-chip communication, we need a laser. This is not a laser yet. But by combining optical engineering with material science, we're a hell of a lot closer. Silicon photonics. Turn off the dark. Thank you.
We'll start with the questions from the judges.
So very nice work. So is heat dissipation an issue here? You have two materials that are that are joined, and then if there's a heat buildup, I could imagine that
right.
A lot of issues can arise.
So you're talking about the heating, for example, from the metal semiconductor system? You're absolutely right. So I'm going to explain that a little bit for the audience, but basically when you have a surface plasmon, when you have this electron light wave system, you're literally driving current, right? Your electrons are moving back and forth, so you're driving current in your metal and you're dissipating heat. And you're right. We actually have some studies that are coming out where we see that we can actually heat this thing by over 100 Kelvin, potentially. And all this requires is better design. We're going to need better heat sinks. So yes, that is something that we need to take into consideration.
Okay, so the really exciting thing about nanophotonics is moving the light, like for an interconnect, right? So you just kind of showed it going around in a circle in one part of your wire. Can you get it to go down the wire and read it out somewhere else?
You're quite right. So metals are lossy. Metals are lossy materials, right? So it's very difficult actually to have light propagate down the metal. But there's no reason that needs to happen. All you need is a light source, right? For example, a transistor has oxides. The oxides can guide that light. Silicon, without the metal, can guide light just fine. Micron distances, more than that. So the point is that by having that metal there, that can help you become the light source. But the actual wave guiding, the actual light guiding, that can be done in any other material. Not a problem.
With a wavelength-sized interconnect?
With a wavelength-sized interconnect, yes.
Okay.
Thanks, Carlos, for a nice talk. I know a lot more about nanophotonics than I did 15 minutes ago.
That was the goal. You learned some optics and did a good job.
So how important are the dimensions and the size of these materials? I guess, is the processing one of the things, or the important design criteria, making this smaller?
Right. Well, we want to make this smaller, first of all, because if you ever actually want to make devices, you want to make as many of them as you can. To give you some perspective, we currently have billions of transistors per centimeter squared, right? The state of the art right now is like an optical chip has actually 4 of these little light sources, 4 chips, or 4 of these little units of logic, and it's like a centimeter big. It's not even nowhere close. So as far as making them small, we want to make them as small as possible, but we can't make them too small, because if you make them too small, then they become quantum confined. So at about 10 nanometers, you start to have effects that are not at all related to the actual materials that you're working with. So we made them small enough such that they might be useful for something, but they're large enough such that they're still bulk. They have bulk properties. So their performance is much easier to predict. Student questions?
Time for one.
Optics.
Come on, you physics people. Going to all right.
Sure.
So clearly the dimensions of these wires are important. How important are the dimensions of the coating?
Very important. So actually, they didn't give you any dimensions. I didn't spend any time talking about that. But the nanowires that we use are anywhere from 70 nanometers to 150 nanometers thick, and they're microns long. Okay. The coatings are anywhere from 50 nanometers thick to 50 nanometers thick. The coating matters, and I said that on purpose, because we're designing optical antennas, right? So the resonance frequency of that optical antenna, like the region in the electromagnetic spectrum where it's actually active, is very strictly dependent on the geometry of the antenna. So I showed you some very nice pictures. These are actually computational simulations of the VNM. And I use these simulations to design optimal optical antennas, optimal geometries, optimal thickness, that would make my antenna actually active in the region where my semiconductor emits light, in the visible range. If you make them a little bigger or a little smaller, they can be in the IR or in the UV. You have to make sure that it's active where you want it to be active. And you have to take into account both material properties and geometry.
All right, let's thank Carlos one more time. Now we'll move into our final presentation of the evening. So I am pleased to introduce Denise Wong from Vijay Kumar's lab in the mechanical engineering department. She received her degree from Cornell University, her bachelor's, and she's going to be talking about robots, micro robots, continuing the theme of tiny things. Fun fact, favorite appetizer is a cheese board. So.
All right, so I realize that I'm here standing between you and happy hour, but I guess a plug is that you can get beer anywhere, but there are only so many places you can learn about microbio robots. So with that, I'll get started. So what am I actually even talking about? So we're actually really talking about truly micro-scale robots here. We take these micro plates that are, in this picture, 40 microns square plates. And just to give you an idea, how small that really is, a human hair is typically about 18 to 80 microns, so we're on the scale of the cross-section of a hair. So that's pretty small. And so we use a microscope like the one below to look at them. So the bio part. So I'm going to be talking about actuation and sensing at the microscale. But it's actually really difficult to have actuation on a small scale, but we have a lot of biological organisms that really strive at the microscale. So that's why we look towards biology for actuation. And so in this case, we use flagellated bacteria. So they look kind of like that picture over there for actuation. And we also use E. coli, which is very well understood for our sensing applications. So in this picture, we're showing synthetically engineered readout of green fluorescent protein. So usually when a bacterium detects some chemical, you don't really see the response, it's internal, but with synthetic biology, we can engineer it so that it emits some kind of green fluorescent protein that we can optically detect. And so the robot part. So if you compare the image on the left to the humanoid on the right, it's arguably a little different. So I'm inviting you for the next 15 minutes to kind of relax your definition of a robot. And so we're doing similar things as this humanoid here, that's macro scale. So we are doing sensing and we are doing actuation, but just at a micro scale, which is a lot different. And we're not quite as far along as the humanoid here. But let's move on. So we're getting there, and I'll show you here. So for the actuation piece, we use swimming bacteria, and so this bacteria that we use are Serratia marcescens, which are really similar to E. coli, which is shown in this picture. So the way that E. coli swim are they have these long flagella tails, about 10 to 100 of them, and then they have a chirality, and they all rotate in the same direction to kind of bundle and propel themselves forward, kind of like the way a screw screws into a piece of wood. And then the way they change direction, as you can see, is one of the flagella switches the direction it's rotating, and then it randomly reorients. So in a free solution, the trajectory of a swimming bacterium is a random walk, and it's difficult to predict. But what we do is we attach these bacterium to a plate, and you can kind of see it doesn't really look like a random walk anymore, and it's a little more organized, and looks like we could almost predict what's going on. So I'm going to step back a little and talk about how we make these. So we start out, we make these microplates using a process called photolithography. So similar to the way that circuit boards are made, we start with these chemicals that we'll spin coat onto a glass slide. So just a show of hands as a kid, how many of us tried spin art? So the spin coating process is actually really similar to spin art. We're rotating the glass slide, and then we are depositing a layer of solution onto it, and because it's spinning, the centripetal forces pull the liquid, and we create a really uniform thin layer. So we do this twice, one layer that's sacrificial, and then a second layer which is our photoresist. So in our case we use SU8. And so to create the shapes, we have this photo mask that has a chrome opaque layer with cutouts of our shapes that we want. And then we lay this on top of our photo mask. We shine a light over it. The parts of the photoresist that are exposed will cross-link and solidify. And then we can rinse off the unexposed photoresist, and then we're left with a glass slide that has a lot of microplates on it. So here we have some squares, but we can really make any shape that we want depending on the photomask. So now getting to the part with the bacteria. So the video I showed you of swimming bacteria in solution, it was not very dense, but we want these microstructures to move. So we want as many bacteria on there as possible. So we grow these swarm plates, and it's on a petri dish of agar. We blot them, and then over time, they swarm like the picture below. So this is a lot more dense than what we saw with the swimming cells. And we literally take our glass slide with our microstructures, and we blot them on top of the cells. And the cells that we use, Serratia marcescens, they naturally produce this polysaccharide, which is sticky. And so conveniently, they'll stick to our plates. So I'm going to show you again this video that I just showed you, and I want you to notice that the micro robot is rotating clockwise. And so after looking at a lot of different micro robots, we noticed that this is actually a bias. There's always this clockwise bias. I mean, occasionally we'll get counterclockwise rotation because of the random displacement, the random orientations of the cells on the microstructure, but most of the time it's clockwise. So before we try to control these microbio robots, we want to understand why is it rotating and where are these forces coming from. So we hypothesize that there are two different cases. So if a bacterium is attached to the center of the microbio robot and the flagella is like right on top of the microstructure here, then we believe there's just one force, one propulsion force that it's exerting on the plate. However, if we have a flagellum sticking on the edge and a cell sticking on the edge and the flagellum is kind of hanging off, you can we believe that there are actually two forces now. One, that's the propulsion force, and another tangential force from the flagella kind of like hanging off the edge of the microstructure and then interacting with the glass slide. So this is a diagram from the back view kind of showing more clearly what I'm talking about. So you can kind of think about this as like wheels on the edge of a plate. So these wheels are turning and they're interacting, and so all the cells that have flagella hanging over the side are going to produce a clockwise force on the microbio robot. So to test this hypothesis, we ran this experiment where we attached bacteria to the top of the SU8 and then also to the bottom of the SU8. Well, what we really did was we just tried to release these structures so that the bacteria would be on the bottom. And so you can imagine that if you had a wheel, as I was talking about before, it doesn't matter if you are attaching to the top of the cells or to the bottom of the cells, the flagella is still going to interact similarly to the bottom slide. And so what we do see is that we have clockwise rotation predominant for both the cases when the cells are attached to the top and as well as when the cells are attached to the bottom. So another way that we can actuate microbiorobots is using collisions with the walls, bacteria collisions with the walls of the MBR. So in this case, there are no cells attached, but the cells are colliding with the walls. And so with asymmetric geometries, we can actually bias rotation directions, such as in the case on the left, rotating clockwise, and in the case on the right, rotating counterclockwise. And so with this, I'd like to change gears and talk about sensing. So sensing on the micro scale. So why do we even really care about this? So what we want to be able to do is distribute a lot of different sensors around a microscale environment to get spatial resolution of, say, certain chemicals. Say we're interested in detecting TNT or maybe a hazardous chemical such as maybe something harmful to the cells. And then, so what we are able to do, what we want to be able to do is have these cells attached to a plate and then use a magnetic robot to push it around to distribute it and then come back over time and say, we saw TNT like in square 1, square 2, but not in square 3 and 4, something like that. So in our experiments, we use UV light to do this. So our input is UV light. And this picture is just showing the way that we can have a magnetic robot distribute these sensor payloads, these little squares. So on the right-hand side, we have 6 different quadrants just to show this spatial coverage that we can get. So how do we do this with biology? So we know that biology is really good at sensing the environment. But if we use synthetically engineered E. coli, we can, but synthetic biologists have gotten to a point where they can kind of engineer different behaviors. So in our case, we're using a E. coli cell, an E. coli toggle switch cell, which is able to take a UV input. So if it detects UV light, it's able to give us an output of fluorescence. So this is similar to the way that electrical circuits have diagrams, genetic circuits also have diagrams. So this is what's shown here. But it's a little confusing for people who don't understand synthetic biology like myself initially. So I'm going to walk us through this. So we start with 2 promoter cells. So the way we get bistability is that you have two behaviors that are mutually repressive. So when one of the activities is high, the other one has to be low. And when one of them, and then you can flip it the other way around as well. And this is done using an external input. So we have 2 promoters, P-lac and P-lambda, and they control a gene each, one gene each. So P-lac controls lambda-CI, and P-lambda controls lac-I. So the protein that's produced by the red gene, lambda-CI, that represses the behavior of the other gene, lambda-CI, that represses the behavior of lac-I, and vice versa. So the behavior of lac-I represses the protein produced by lac-I inhibits the activity of lambda-CI. And so when we don't have any external stimuli, they both have a basal level of behavior. However, when we input IPTG, this chemical, this can flip the toggle switch onto a low state because it inhibits the production of a protein lac-I. So it's essentially kind of disabling one side of the switch by flipping it to a low state. So this is the state that we initiate our cells in when we turn on the biosensor. So if we remove the IPTG, this low state is stable and it stays in the low state. So for visual purposes, I'm going to visualize the lambda CI protein that's created. And when we take the cell and we shine a transient signal of UV light onto it, it breaks down this protein, and so there's now nothing to repress the behavior of this LAC-I gene. And so the activity of the LAC-I increases. And so now we're at a high state, and we call this high state because a high activity level of the gene LAC-I is linked to production of fluorescence, GFP, which we can detect optically. So this is the way that the toggle switch gene works and our biosensors work. So this is a video showing the cells in action. So the cells were exposed, and then over time, the fluorescence can be detected. So that was an experiment from a biology lab. But as roboticists, we were like, okay, great, these cells work in an idealized environment where they're grown in agar and they are full of nutrients, but we want them to work on these small SU8 plates. We want to be able to push them around with our magnetic robots. So one of the great challenges with I guess coming from as a robotics background is understanding the biology and dealing with the stochasticity. So the result on the left shows the difference of the off state or our control where we don't expose the cells at all, and then on the 10-second image where we do expose the cells. So it was great when we were able to see that we got significantly detectable optical differences after looking at 20 or so cells. So these are just images, microscopy images. And then as a comparison, what biologists look at when they're looking for fluorescence is they actually put these cells through a flow cytometer, so they can basically, with this large machine, take cells individually and look at their intensity. So we get the same result. We're showing quantitatively the same result, but just a different way of looking at the same result. So with that, we attached these cells to small sensor payloads, and then we can see that on the left-hand side are sensor payloads that have been exposed to UV light, and then on the right-hand side are sensor payloads that are unexposed. So you can also see here that we have a lot of false positives and false negatives on the cells. Like sometimes not all the cells will turn on for the exposed sensors, and that's because we're kind of taking the cells out of their happy environment, and so they're going to behave differently. We're using different growth mediums. They're attached now to a different surface, and as biologists know, or anybody who's worked with cells, any of those things are reasons why a cell won't behave the way that will change their behavior. These environments will change their behavior. So we've taken this biosensing and integrated it with this magnetic robot to create a system where we can detect, we have spatial resolution for UV light, and we believe that now that we've integrated this with a synthetic cell, we can actually go back to the biologists and say, well, we want to detect different things now. Can you give us a cell that detects, say, TNT? And we would be able to do the same thing on a similar system. So in the spirit of the iTalks, I wanted to talk to show you other research that have used micro robots. So in this work, we're showing that we can test protein-protein interactions. So this is work from our lab. It's not something that I specifically worked on, but here we're showing different interactions that you can coat beads with different proteins and push them into a region here that has, say, protein A, and then the beads are coated with protein B, and you can test to see if they interact. If they interact, then they'll stick, and the robot can't push them any further. And then another application is for directed drug delivery, where we can autonomously drive these magnetic robots to pick up a bead and then drive it to a a goal position autonomously using camera feedback. So these are just some examples where micro robots can be applied, and I'd be interested in talking to any of you if you have any additional ideas on how we can apply them, because I think it's an exciting area, especially either for research as well as applications, perhaps in directed drug delivery. And so with that, I'd like to thank my collaborators, Elizabeth Beatty, Dr. Edward Steger, our advisor, Professor Vijay Kumar, and our collaborators at MIT, Deepak Mishra, and Professor Ron Weiss. And this work was funded by the Office of Naval Research. So thanks for your attention, and with that, I'd like to take any questions.
We'll start again with the judges.
Thanks, Denise. That's an interesting talk. So you're using magnets to move around these micro robots,
right.
But you have these bacteria attached, at least in some cases. Can you use the bacteria movement? Can you drive or guide its movement in response to some sort of chemical signal, some gradient of a chemical factor, or are they purely just random motion?
So there has been work that has used say chemotaxis to drive robots around. We haven't done that in our lab, or I haven't done that personally. So what we're hoping to do, and work that I haven't shown, is you can actually use blue light to change the behavior of the cells. So instead of having a like 10-to-1 ratio of run and tumble, if you shine them with blue light, they actually tumble all the time. So you can change the forces that are exerted. And so we're hoping that we can build at least a short timescale model to be able to predict, say, 5 seconds in advance, and then use some kind of a blue light to drive the micro robot around.
Thank you.
Thank you, fun talk. So there are these magnetic bacteria, right, that have these little magnetic chains inside.
Right.
So that would give you a handle for aligning them before you put them on your plates, and then you wouldn't have this problem with them being randomly oriented. Or do you have a better way of aligning the bacteria on the plates for future work?
So we've tried alignment of bacteria. So we've tried a couple of different things. We've tried flowing the cells and then sticking them on, because bacteria seem to like to align with the way that water flows. We haven't had a lot of success with that. We've also tried putting channels in and then having growing cells in the channels, because cells like to align to the edges, but we haven't had great success. So what we're actually trying to do right now is understand how the distribution of the cells affects the behavior of them. And so just look at the cell, image the cell, say count the bacteria, and then say it's going to move this way. And since we can make about 10 of these, it's easy to make a lot of them at the same time. We can just look around for a preferential distribution and control that one instead.
Okay.
If you want to go from two-dimensional motion to three-dimensional motion, what do you have to do, and what are the challenges?
So with magnetics, if we wanted to go into 3 dimensions, we would need more axes of magnets. So that's an active area of research right now. And a lot of people who do that, they actually use thicker solutions to damp out the behavior, because otherwise you're going to be pulling things really quickly. So that's one way of getting 3D motion. And then another way with bacteria is to attach your cells to, say, a sphere or something. So with surface tension, I think that's why our plates tend to stick to the bottom, and so it's a lot easier for imaging, and that's why we do that. But we've actually tried to attach them to thinner rods to try to get directed motion, and they just fly everywhere. So we can get 3D motion, but we just can't really track it right now.
Question from the audience. I'm looking at you, Robert. Or anyone else. In the back?
So what determines the virality of those bacteria? Is it fixed? Means the bacteria that it has in the slide, they have a fixed virality, like left-handedness and right-handedness, and what determines?
So all E. coli cells, they always all have the same chirality. I don't know if there are any other cells that have different chirality, but in an E. coli cell and in Serratia marstensins, which is what we use, they're always the same chirality.
Left or right work is fixed.
Right, it's fixed. And so when they're rotating all in one direction, in the clockwise direction for Serratia marstensins, then they'll bundle together, and then if one of them flips, the whole thing just unbundles.
All right, thank our speaker one more time. So before everyone goes, I just want to thank our judges for volunteering their time. So we had, you've already heard their voices asking questions, but now I'll actually introduce them as I should have previously. But we have Professor Jason Burdick, my actual advisor, so I'm on my best behavior. Dr. John Crocker, Associate Professor of Chemical and Biomolecular Engineering, and Dr. Dae-Yoon Lee, Associate Professor of Chemical and Biomolecular Engineering. So if we can get a round of applause and thank you for the time. So this was the first round. The second round will be April 2nd, so there'll be 3 more talks, and then based on the judges voting, the winner will be announced then for the overall $500 prize, but there is still a $100 prize at stake. So in American Idol type voting fashion, we'll have the boxes up here, write your name, and then put it into the box before you come down, and then leave it with your audience favorite. And happy hour is outside, so thank you.